All right. Hello, everybody. My name's John Linford. I work for ARM, and I'm here with Jeff Wittich, who's the Senior Vice President for Ampere, and we'll be talking about running HPC in the cloud with Ampere Ultra processors. So, Jeff, do you want to tell us a little bit about this new Ultra?
Sure, I'd love to, John. Thanks. So when we designed Ultra, we really focused on three different design elements and value props. One, we were focused on predictable high performance. Two, focused on high scalability. And three, power efficiency. So the whole Ampere Ultra product family delivers on those three attributes. From a predictable high performance perspective, it was important for us to deliver the highest possible core count at a very consistent frequency. That way, you had many, many resources that could be utilized for high performance tasks. And you could expect the same level of performance regardless of what task is running, or in the case of a multi-tenant environment, regardless of how many users were actually running or how many applications were running in the system. And we delivered those up to 128 cores via a coherent mesh-based interconnect. So very high bandwidth interconnect to feed traffic into and out of those cores. And then obviously memory bandwidth is super important as well. And with 128 cores, we need a lot of memory bandwidth. And so we're delivering up 8 memory channels, which are capable each of supplying 2 DIMMs per channel at up to 3200 speed. These are DDR4 DIMMs. So very high memory bandwidth platform feeding a lot of cores, which leads to a tremendous amount of scalability. And one of the key metrics in the cloud is the number of cores that you can deliver in a specific rack. More cores means either more applications, more users, more performance in a given space, in a given power envelope. And so we've got the world's leading cores per rack for the highest performance solution. We also support 2-socket systems. So we utilize C6 for cache coherent multi-socket support. And then also importantly, as we scale out, is that we have a lot of attach for I/O. So we support PCIe Gen 4, and we have 128 lanes on a 1-socket platform, 192 PCIe Gen 4 lanes on a 2-socket platform. So really an extreme amount of attach for accelerators, for storage devices, for whatever your workload actually requires. And then also, power efficiency is super important, and that's important whether it's because you're looking to reduce OpEx or whether you're looking to just scale out in an existing infrastructure footprint. So we have the world's lowest power per core for a data center product, and we did so by creating a very, very efficient design based on the ARM architecture, and also utilizing TSMC's 7-nanometer process, and doing all this in a monolithic die to reduce power, to ensure maximum performance, to reduce bottlenecks in what is an extraordinarily scalable system. And last, we've also built in all of the advanced power and security management features that you expect out of a data center class processor. And so the net of it is that we've ended up with what we're calling the world's first cloud native processor. It's really the perfect fit for any type of workload running in the cloud in an extraordinarily scalable manner.
That's excellent. So extremely high bandwidth, high core count, and ability to scale out securely. That's a really powerful platform there. I love it.
Yeah, we think so too.
Consistent high frequency across all cores. So this means that you're able to maintain a very high rate of performance, integer performance, floating point performance, even as the workloads scale up. Is that right?
Right, that's exactly what we're delivering. So we're able to deliver the maximum frequency when all the cores are running across a wide variety of workloads. So you don't have to worry about perhaps your workload going and maybe running specific instructions that then push the frequency down a whole lot, and then trying to manage that over time to make sure that every time you're utilizing those instructions, you get the maximum possible performance out of it, because everything else suffers because the frequency is slower. With our processor, you're just running all out all the time in a very predictable manner. which produces the greatest possible throughput, especially when you consider the massive number of cores we have with up to 128 on Ampere Ultra and Ampere Ultra Max. And so that type of throughput performance was incredibly important to us as we designed Ampere Ultra.
That predictability is really valuable. I know that scientists for a long time appreciated architectures like the Blue Gene because of its runtime predictability. So this is going to be very interesting, I think very compelling as people are able to get their hands on it. You also showed GPU accelerator here. So having that scale out at the core level is fantastic, but then there is an option if you really needed to do some heavy lifting on float intense workloads. It sounds like you could attach a GPU as well.
That's right. That's right. With a large number of PCIe Gen 4 lanes, it just gives you a ton of flexibility for connecting up GPUs or other accelerators. With having a lot of by 16 connections, you could really load the system up. So like you said, it kind of gives you the best of both worlds. You can do a tremendous amount of work on the CPU cores themselves. You can also offload out to GPUs. We've got broad support for a number of different accelerators. And so really creating that right balance in the platform is really important to us. Having a lot of cores is great. You need a lot of IO to feed them. You also need a ton of memory bandwidth as well to feed those cores so that they don't get starved, especially for these types of, HPC tasks in the cloud.
Fantastic. Well, let's take a look at some of the benchmarks then. All right, so Ampere was kind enough to send us a few engineering samples of the upcoming 80-core part in a dual socket configuration. That was the Mount Jade server. So we were very excited to get our hands on these and take them out for a test drive with a couple of representative HPC benchmarks. And the way we looked at this was we're targeting commodity HPC workloads that are really the driving force behind the majority of the HPC market. The vast majority of the top 500 systems are not in the top 10, of course. There's the 490 systems behind them that are workaday systems at universities and labs, and that's really where most of the innovation happens. And as it happens, we feel that this chip is a good fit for that type of workload. So we approach this from a perspective of, if we could get a scientific result from a representative code quickly and then compare it to, say, a cloud-hosted CPU, and how would those stack up? So we took a look at the SW4 Lite seismic wave model. And as you can see here, we are about 10% faster than even the Intel's second generation Xeon processor in the C524X large instance from AWS. And we were able to get to this point with no tuning whatsoever. It was quite simply compilation and run. And by doing just compile and run on the same platform, we were able to get this very competitive performance. Likewise with the WRF model. WRF has a lot of knobs you can turn in balancing processes and threads. So we did look a little bit about what is the optimal way to decompose that parallel workload on the Ampere. Having 80 cores means that we were able to break this up into a lot of different ways. But within an hour or two of simple testing, we were able to get almost 42% speed up over the Intel processor again. So very competitive performance, I think, from WRF. Next slide, please. Other workloads we took a look at, so computational fluid dynamics. This is a critical area for many industries, including aerospace, defense, you name it. There's probably CFD involved somewhere. In this case, we took the SimpleFoam solver from OpenFoam, and we found that it was about 33% faster than the comparable Xeon core. In all cases, I should mention, we are using a GCC compiler. So of course, there's always room for improvement in these kinds of benchmarks. But again, what we're trying to demonstrate is out-of-box performance with no tuning from the perspective of someone who simply needs an answer quickly. And we're seeing that this is a very positive result, very, very good results with very little human effort required. We also took a look at geodynamics code, so a couple of codes from oil and gas. SpecVim 3D is an excellent representative code here. And we were able to take it out to 2 sockets on the Ampere platform. Running on a single socket with 64 threads or cores, it pulls about even with the x86 offerings from AWS, but we can continue to scale up. And in 2 sockets, we were seeing a 60% performance uplift over the x86 baseline. And again, this was without tuning or special compilations or anything, and done on engineering samples. So I think this is a very promising start, and I'm looking forward to trying these in production and really putting them through a competitive and a rigorous benchmark in the days to come.
Yeah, John, these look great. Being able to see Ultra out there now actually matched up head to head with some of the leading instances in the cloud for HPC and these types of amazing out of the box performance. This is really great to see. Awesome work. So one thing that I also wanted to talk about is how Ampere Ultra is able to flexibly match the needs of your data center. What we were looking at there were results from our 80 core 3.0 gigahertz SKU, but we have a number of different SKUs out there that are able to simply match the needs of your data center. So whether you're looking for a specific TDP point because of your rack power limits or thermal constraints, whether you actually are looking for maybe a lower core count processor because your primary concern is memory bandwidth or GPU attach, and you want to make sure that you utilize all of the existing budget within your rack where you want to use it, whether that's 4 GPUs or 4 CPUs. We have a very flexible range of SKUs ranging from 32 cores, which is a great option if you wanted to actually do some work out at the edge, and then moving all the way up the stack up to our 80 core peak performance processor at 250 watts. The thing that also makes this all very simple is that all of these SKUs have the same attributes. So they all have the same amount of total L3 cache. They all have the same L1 and L2 cache per core. They all still have 8 memory channels, 128 PCA lanes per socket. They all support 2 socket. So you're not making any compromises as you look to make different decisions for your specific environment. You can go ahead and just pick the right SKU for you. And it makes this very easy to compare across SKUs, very easy to deploy in a super flexible manner. Even a heterogeneous environment where you've got different SKUs deployed won't be difficult to manage because they all look the same from a feature set perspective, and they're all very high performance as well. So that was very important to us, is to create just simplicity and really create options just where they matter for end users.
Excellent.
Yeah, and John, I think you mentioned that you guys were using the Mountain Jade platform, which was our 2-socket platform from WeWin. We actually have a number of different options out there that are really ready for deployment now. These systems are already available from WeWin and from Gigabyte, as well as actually some other ODMs and OEMs that are coming online right now. And these are deployable now in customer environments. So we have the 2-socket platform, the Mountain Jade platform, which is what you can see here on the left side of the page from WeWin. And then we've got a 1-socket platform from Gigabyte that we're calling Mount Snow, and that's there on the right side of the platform. There are a number of different options at the platform level for supporting more physical GPUs, which is what you can see down there at the bottom right. So a 1-socket platform that has even more room for by 16 large GPUs. And so in addition to WeWin and Gigabyte and these lead 1-socket and 2-socket platforms, we also have a number of other platforms that are in development right now. A couple of other 2-socket platforms, especially in China. You'll hear a little bit more about what we have in the works there, but those are right around the corner. And I think we'll provide the flexibility at the platform level now to meet the needs of whatever anyone's looking for in the HPC in the cloud space. So they're all available, 1U, 2U, and then the full range of attach options from a memory and I/O perspective. So lots and lots of ways to go ahead and get started today with the Ampere Ultra processor in HPC.
And I might mention, so speaking as a sysadmin, we received our Mount Jade servers, and we have a lot of experience with different kinds of servers from all over the world, implementing every kind of strange hardware you might imagine. These were fantastically simple. It was just plug them into the cluster and they pixie boot and we were going. It didn't take any special requirements. All the basic stuff you would expect from a BMC, from an ILO, everything there is there, and it worked the first time, which as a long time person in this space is very much appreciated. So it's a good experience just installing and getting these things off the ground.
Well, that's great. That's great to hear, John. That was one of our big goals going into this, is try and make it very easy for people to adopt this, very easy to turn it on, to get going. And like you mentioned earlier with the performance results, that was out of the box. So just imagine you get one of these servers, you plug it in, you put it in your cluster, everything just works, it boots. You can run your application, you get great performance out of the box. It's not a big heavy lift to actually get going on Ampere Ultra. And so that's exciting to see that was your experience as well.
Yeah, very pleasant.
All right, well, thanks a lot. I know we're excited here at Ampere about our Ampere Ultra processor family. Excited to get more information out there for everybody over the next couple months, more benchmarks, more platforms, more releases. But as I mentioned earlier, these platforms, they're available today. We designed these for the scale out cloud for throughput computing, and so it really makes it a perfect choice for those who are looking to run HPC applications in the cloud. This is really a no-brainer in terms of scalability, performance, efficiency, just really leadership across all of the key vectors.
Great. Well, thanks for showing us, Jeff. I really appreciate it. And yeah, good luck to you. Thanks again.
All right. Thanks, John.
Bye.
Bye.